This is FE Peer Review. The date is the 29th of November 2021. Auckland, New Zealand long distance observation. Thanks to Ranty for the suggestion. This video came about because of a comment that Ranty put on his community board. I'll put a link to his channel in the description. Thank you again, Ranty, for the idea. Hello everybody. Ranty put up this little note on his community board about a video of a long distance observation, and he gave the link to it and said, anybody want to go at it, they're welcome to. So I'm going to go at it. Here's the video. I'm not going to show you all the video, but here's the main points of the video. The observation is from a beach in Auckland, New Zealand, looking past a lighthouse that they list as 5 kilometers away, past a container ship they estimated 15 kilometers. We're going to take that distance with a grain of salt, as they did themselves. They estimated that just simply based on the distance to the shipping lane. And then finally, the distant target is a little island called Tiritiri Matangi, 25 kilometers away. And I'll show you one more image. Here we have the lighthouse, the container ship, and the island in the distance. And as we see, the top of the island, the ridge that runs along the top of the island, is just about even with the top of the ship. There's a bit of a few little bumps over here. So what we're missing here is the height of the observer. But based on this image, with the water line visible, I'm going to estimate the observer's eye level at 3 meters. I'm assuming the observer's standing, putting their eye level 1.5 to 1.8 meters above the ground. And then there's some additional slope down to the water. So I'll call it 3 meters, keep the numbers easy. So we're looking at the Rangitoto Lighthouse. Here's a picture of it. According to Wikipedia, the focal plane is 21 meters or 69 feet above the water. That would be up here. So 21 meters is the value I will use. And if we look on Google Earth, the lighthouse is right where I'm circling the mouse. This piece of rock over here, this little peninsula, is called the Takapuna Head, and we see that in the video. And the location seems to be somewhere along this stretch of beach, based on the line of sight from the beach past the lighthouse to the island. The island is out here, Tiritiri Island. Again, this little plateau on a topo map we'll look at shortly. This little plateau is at 80 meters above, and this ridge that runs along here varies between 60 and 70 meters. I'll take us to the topo map. Here's the topo map. There's that little plateau of 80 meters where I'm circling the mouse, and then this is the ridge line here. The yellowish colored, orangish colored topo line here is the 60 meter line, and this is a 60 meter line, so it's right in between. It's just above 60 to 70 meters. That gives us the height of the island, the height of the lighthouse, and the distance is, I got 25.5 kilometers for this path line. Bring this down here. 25.5 kilometers for that line. So I'm going to use that rather than 25. And I got, I think it was just under 5 to the lighthouse, 4.8 kilometers to the lighthouse. So those are the horizontal distances that I will be using. And we're going to make a model and do a little bit of math. Here's the island. And going from Google Earth, there's a ridge running down the middle of the island that varies between about 60 and 70 meters. There's a little high point down at this end, which is at about 80, and a bit of a dip right in here where it goes down to about 60. I checked this against a topo map I found online, and that map looked quite accurate and pretty much matched the Google Earth value, so I'm going to go with the 65 as a sort of typical height for that ridge. Now what we have here is the start of a SketchUp model in which I've modeled the location, the observation point down at the bottom left, the lighthouse, the ship, and the island. The Distances between them are shown with dashed lines: 4.8 kilometers, 15 kilometers, 25.5 kilometers. Our island has a height to the ridge line of about 65 meters. Well, 65 meters, which is approximately from the map, from Google Earth and the topo map. Here we see the ship. Now, I've drawn containers based on a standard size container. Their standard height is roughly 2.6 meters high, and I've stacked 8 of them. There are actually 5 visible in the photo, but then there's also the deck on the hull of the ship to account for, and based on the photo from the video, I approximated that as being equal to roughly 3 containers in height. And then we have the lighthouse, which we got as 21 meters. And then finally our observation point, which I set at 3 meters above the ground surface. We have a little station point marker here. And the center of that circle is 3 meters above the ground. And then what I've done is I've created a scene where we're going to look through that. We're not actually going to see the station point because our eyes are going to be right at that intersection, looking past the lighthouse, past the ship to the island. Now this is all, go back out for one more thing here. This is all based on a flat plane. So everything has its base on the same flat plane. Here we are, looking at our lighthouse, the ship, and the island beyond. And as you can see with the ship, we see all 8 containers. Nothing is hidden below a horizon line. So this suggests a flat plane all the way out to the island. And the island looms above the ship by almost half the height of the ship again. So the next thing we're going to do, now that we've looked at a flat scenario, is we're going to do some calculations to determine that if the ground surface is sloped per the standard Earth curvature figure, how much drop is there between our observation point and each of these 3 locations. We're going to determine the amount of drop and then adjust the model by lowering each of those 3 items that equivalent amount. And I'm going to do the same with this ground surface. That'll be our next step. Now, most of you have probably seen this Earth curve calculator. This one has no provision for refraction in it. It's purely geometric. They call it an Earth curvature calculator, but basically it's just a circle calculator or a sphere calculator. And you see the diagram down at the bottom. The reason why they call it an Earth curvature calculator is because they've built into it the radius of the Earth, 3959 miles, 6371 kilometers, and that's a fixed value that can't be changed within this calculator. So if I go up to the distance section and type in 25.5 for my distance to the island, it gives me 51.03 meters of drop. This is no consideration of eye levels or anything or hidden distances. This is just simply the distance h down here at the bottom of the diagram, h. Well, what I've done is I've made a little Excel spreadsheet. I did this last year, found it quite useful. It's exactly what's written down in the bottom here. It's very easy to check it. So what I've got is I've got the Earth's radius in this cell here, and then I type in the distance, d, 25.5, does these equations, gives me the h value from their diagram, which is the drop, and it gives it to me in kilometers, so I multiply it by 1,000, thank you Nathan Oakley, to get meters, 51.03 meters, and as you see it matches their results. So that was a nice way to check that the calculator actually works. Now I've done this because I can, if I choose to, I can put any value in here for radius, if I want to use it for just looking at any circle. And of course, 6371 is no refraction. And when we go back to our SketchUp model, we're going to be building it based on no refraction. But then when we're done with that, we're going to do yet another one with refraction. And for that value, I'm going to use 6/5R. And the reason for that is that's a standard refraction value for the land-sea interface. It's often said that surveyors use 7/6R, which they do, but that's a value that's used over land for long distance observations over land. But when you get to the land-water interface, i.e. the beach, you often have higher refractive conditions because of the differences in the atmospheric layers due to land versus water. So we'll use this for both a no refraction observation and a refraction observation. Now I've plugged in the values for our three distances already. 25.5 kilometers gives us 51 meters drop. 15 kilometers gives us 17.7, and 4.8 kilometers gives us 1.81. And that's what I'm going to put into the SketchUp model now. And you can watch me do that. So what I'm doing is I'm live modeling in SketchUp, and I've put that into the video here at 1.5 speed. I sped it up a little bit, and then I'm just narrating over it. So I'm taking the three drop values from the spreadsheet, and I'm just simply moving my object down by the appropriate amount according to that drop value. And at the same time, I'm taking that flat plane that I had drawn, and I've drawn lines across it, and I'm just dropping those lines down. So this is a crude approximation of a curved surface. I haven't bothered to try to curve the actual ground plane in between the objects. I'm simply running them as a straight surface from one object to the next, and then just making sure to get the correct amount of drop into each one. So there I've dropped the ground surface at the ship, and now I'm going to check the height, make sure I did it correctly, and then drop the ship down as well. And then finally we're at the lighthouse. Repeat the process. Start by dropping that ground surface line 1.81 meters. Here I am selecting the line that's going to go down 1.81 meters, and then I'll check it and move the lighthouse down to match it. And then finally, we're going to go back to our original viewpoint and take a look at our results. And what we see is that the island does loom up a bit over that ship. There's a bit of missing cargo containers there, and the lighthouse is approximately over 3 times the height of the island. Now I've reset the model back to a flat plane again, and I'm showing in the spreadsheet here that I've inserted the new radius value based on 6/5R for Earth, and I have calculated new drop heights for the 3 objects. You see them highlighted in the spreadsheet. I'll use those values now, and as expected with refraction, those drops are less than we saw before. So here I am, I'm just going to go in and adjust the heights of each element. First the lighthouse, then the ship, and then the island. And as before, I am running the live modeling at 1.5 times the actual speed. Now we will return to our original viewpoint and look at the new arrangement of objects so that we can compare it with the previous 2 views. What we see is that the island rises above the top of the ship some still, and it's rising up the height of the lighthouse, but it's no longer 1/3 of the way up. It's higher up than 1/3. It's not quite 1/2. I'm estimating it's 2/5 of the way up, around 40%. This is all consistent with what we expect to see on a globe with refraction. Let's see what kind of conclusions we can draw, if any, from these images. It was an interesting exercise. I have overlaid the 3 SketchUp model images, flat Earth, globe Earth, no refraction, and globe Earth, and I've overlaid them on top of the image from the video. Here's the video image. And we'll start by looking at the flat Earth SketchUp model overlaying over the photo from the video. So I've got the bottom of the lighthouse and the top of the lighthouse in the SketchUp model aligned with the top of the light fixture on top of the lighthouse, not the top of the tower itself, but up higher, because that's where the height to 21 meters was measured. And what we see is this green band is our island, and it is, in the SketchUp model, flat Earth version, considerably higher than how the island actually appears in the photo. So that means that something, if the Earth is flat, something is causing that island to appear much lower than it actually would if light travels in straight lines. So what we've got is that it's dropping. Now, this is not typical of atmospheric refraction conditions, which have been measured literally thousands of times. I have several videos on the subject of atmospheric refraction, and they included links to papers and studies and manuals from various industries, also the US military, explaining atmospheric refraction and how it works. So I'm not going to refer back to all of those, except to say that refraction raises things on the horizon. It doesn't drop them except under the most rare and extreme conditions, when and only for short periods of time. So we need a really strong explanation for why the top of the island, the ridge line of the island, appears much lower than it should on a flat Earth. Now let's compare the flat Earth SketchUp model to the globe Earth without refraction model. We see that on the globe Earth, the top of the island is much lower, and we see that the cargo containers have dropped as well. May not be able to see it on the screen so well, but I can see it well on my computer screen. Of the cargo containers, we've got 5, almost 6 containers visible, but the bottom container is slightly cut off. And if you recall, the model contained 8 containers. Let's compare this to the original photo from the video. We see that this puts the ridge line too low compared to the photo. Okay, now let's go back to the globe Earth with refraction view and compare that to the globe Earth with no refraction. We see that with refraction, the ridge line comes up a little bit. Refraction is raising the ridge line in our view. And it's also raising the ship a little bit. Instead of 5, almost 6 containers, we now see about 6.5. 1, 2, 3, 4, 5, 6.5 containers. So we're seeing a little more of the ship as well. Now I think it's only fair to point out, now this is globe Earth with refraction. So this is what we globies consider to be the correct model in principle. And I think it's only fair to compare that to the photograph, because there are some discrepancies, and I'm going to talk about what they are and why they might arise. So I get the opacity right here. Okay, first thing, we see that the ridge line in the photo is indeed higher than the ridge line in our model. So I used 6/5R for the refraction index when I made my model. That's standard refraction. I think it's apparent that with all of the heavy miraging we're seeing in this photograph, that this is not a day when standard refraction is an appropriate measure. I think we're seeing a much stronger atmospheric effect in this photo than is accounted for in the 6/5R. Something else to mention when you're seeing heavy mirages like this is that not only might the horizontal banding of atmosphere be causing issues as far as refraction. But from the island to our observation point, there may also be variations in conditions, which would complicate this further, because something further away would be passing through a variety of atmospheric changes in conditions, whereas something closer would be passing through fewer. Examples of that are a cold current moving through a warmer body of water, cooling the water off relative to water on either side of the current. That's just one example. There can be many things like that going on. And when you have a lot of miraging, that's generally a red flag on that score. So that's one possible source. Another is just simply the accuracy of the model itself. The photograph shows 5 containers stacked, and then it's impossible to tell how much of the hull of this ship is above water. So I had guesstimated that maybe another 3 containers worth was above the water. But if you actually look at photos of container ships, there's a whole lot of variety on that score. For example, this photo here on the right, we have 9 containers stacked. And then from the bottom of the lowest container down to the water is probably another good 7 or 8 containers. So that's a lot more hull coming up out of the water than I accounted for in the model. And you'll find that's the case in other ships. Here's 4 containers. Here's 5 containers stacked. And we've got about 4 below. So not having accurate measurements of the ship itself means that it's impossible to construct a model that's going to be an accurate representation of that ship. This is why measurements matter. Another point, the person who made the video pointed out himself that he didn't know the actual distance to the ship. He estimated it at 15 kilometers based on how far away the shipping lane was. But that does leave a fair amount of room for variation in the distance. So we could be a kilometer closer. I don't know how wide that shipping lane is, but it's probably wide enough that it could introduce a certain amount of error. So these are some of the sources of possible error, which make an image like this very difficult to draw conclusions from. But one conclusion we can definitely draw: in both of the globe Earth models, with and without refraction, we saw that the ridgeline was at or below the ridgeline of the photo, which conforms with what we know currently in the science of refraction, whereas the flat Earth model shows the ridgeline much higher than the photo. And we don't have science supporting refraction that would claim that refraction causes the island to sink. I've done a lot of videos about refraction. Several of them I've included links to literally 12 papers, manuals, and scientific papers on the subjects of refraction coming from various industries and also the US military, and they are universally based on a model in which refraction causes things to rise up rather than sink. So if you're a flat earther and you're going to make a claim or resort to a model that claims that refraction causes things to sink, you need to show where the science is to back that up, because I haven't been able to find it. I'll put a link to 1 or 2 of those videos in the description. So flat earthers watching this photograph poses a couple of problems for you that you're going to need to explain. One is what I said about refraction. We need to see the science to support a refraction model that causes things to sink. Second is perspective. I've heard people describe some kind of effect of perspective causing things to drop. Well, now, I used the phrase linear perspective earlier in this video, and that phrase comes from the concept that light is traveling in a straight line from the object to your eye, and linear perspective is organized by using straight lines between the viewpoint and the object. Now, from what we know of refraction near the horizon, over water, we do get a bit of curve. That's what refraction is all about. However, it's curve that, as I pointed out, lifts rather than drops objects. So even in the natural real world, linear perspective doesn't 100% apply here. But the perspective effects I've heard described by flat earthers are 100% upside down and contrary to what we see in photos like this. There's no explanation for why something will drop, in our view, more than it would if the light was traveling in a straight line, unless you can prove a refraction effect happening. Perspective doesn't exist. Perspective doesn't exist in the sense that it's not some sort of a natural force. Perspective is a way of describing the line of sight. That's all. Describing the line of sight. So if you're claiming that this line of sight curves for reasons other than refraction, then you need to show that for real. You need to give us real, physical, real world examples that show the line of sight curves regardless of refraction. And then you also need to explain, if you're going to use refraction as a excuse for why the island drops, you need to show how atmospheric refraction causes things to drop rather than to rise up. These are some of the challenges facing you if you're a flat earther and you want to use this image to support your claim, because at present it doesn't. As far as whether it supports the globe Earth claim, well, we were lucky to have science on our side, because I use standard refraction in making my model, and this is not a standard day by any means, judging from all the miraging. So I can just say, well, more refraction, and I could lift it up that way quite easily, and I'd probably be right. Now, there's the problem of the ship, but the problem of the ship is not one of the model. The problem of the ship is that we don't have the proper dimensions for it. We need to know the height from the hull, from the deck to the waterline. If I was going to carry this analysis further, I'm not going to bother, but if I was going to, I'd try to find pictures of container ships in the port, wherever this port came out of, and see if I can find ships similar in scale to this one and get measurements from that. The other thing I do is track down in detail where this shipping lane actually is and see if the 15-kilometer estimated difference is correct or not. I have a feeling it may be an overestimate of the distance. These are things I'd do if I thought this observation was worth some additional time. I don't. I think it's fine. I think it's fun to look at. And I don't think the globe earthers are the ones that have any explaining to do in this case. Okay, I've decided to insert this at the last minute. I was bothered by that shipping lane business. Here's Auckland. There's Auckland down here. And this seems to be the shipping harbor that can accommodate container ships. Now, if we look at the whole stretch of coast here, the view is from a beach where I'm circling the mouse past the lighthouse towards this island. This whole length of coast here has no harbors, no ports suitable for shipping containers. So that ship must have originated from this port here, and it must have come around here and gone out that way, like that. So the beach here, Cheltenham Beach, is where the observation was taken from. I'm going to draw a line here from Cheltenham Beach, and it was going past the lighthouse. There's the lighthouse, and the ship was visible behind the lighthouse. So I'm going to draw that line all the way out to the island. So the question is, the path that ship took, what point did it cross this yellow line from left to right? Now, the person who made the video said 15 kilometers. From the beach to the lighthouse was 4.8 kilometers. I can't find an actual map of shipping lanes, but I'll draw a circle of 15 kilometers. "15 kilometers would be right there. not having a map of shipping lanes, I think it's entirely possible that that ship is considerably closer than 15 kilometers. I don't know if this dashed line is actually representative of what these ships actually do or if it's just diagrammatic, but that would put the ship at more like 10 rather than 15 kilometers. So I think that's probably the largest source of uncertainty in that image is the actual distance to the ship. Okay, I just wanted to share that. It's all a part of figuring out how to do good quality observations, and I think what we can take away is that the information provided from that photo is both inaccurate and inadequate to draw strong conclusions. And this emphasized the importance, if people want to do observations like this, the importance of documenting them well. You know, if a flat earther wants to take that video image and make something out of it, what they need to do is go down to that beach themselves. Find somebody in New Zealand to work with them. Go down to that beach themselves. Do it over the course of many days during different weather conditions, hot days, cold days. I mean, you don't want to go on foggy days, of course, but do it when you're going to get a whole range of atmospheric conditions, a whole range of refractive conditions. Use the best quality photographic equipment you can get your hands on. Document the distances carefully. And compare many images to see what kind of patterns emerge. Is there ever a day when that island appears as high as the flat Earth SketchUp model suggests it should be? Is there ever a day when it looks like that or not? I think you'll be really hard pressed to find one. But if you do, good for you. It's not proof of anything, but it's one more data point. So, flatties, my flat Earth friends, what's your explanation for why the ridge line is considerably too low based on a flat model? Love to hear it. And Ranty, thank you for the idea to put this video together. And to all of my wonderful viewers and subscribers, I wish you all a wonderful day. Remember, click that like button. That's what it's down there for. Bye-bye.